So this week, we are very pleased to have Professor Sandeep Pradhan from our department as a speaker. So he did his PhD in the ECS department at UC Berkeley in 2001, and he has been a faculty member at Michigan since 2002. So his research interests are broadly in classical and quantum information processing. Today he will tell us about the quantum Bayesian framework for efficient storage of quantum information. So please join me in welcoming the speaker.
Okay, all right. So this is, I want to talk about, quantum Bayesian framework for efficient storage of information. Typically what happens is when a quantum talk, half the time you spend introducing all the concepts, right? But this is an educational seminar, so I want to keep it as easily accessible as I can. So even if you don't know much of quantum, you should be able to get quite a bit from this talk. And in fact, it may have consequence even for classical, because it's something that's motivated from quantum, but it could be useful for classical estimation theory. It's a new take on estimation theory, you could say, in some sense. So the experts here on estimation detection could comment on it, the significance. We have used it for the lossy problem, but this could be useful for any estimation technique. All right, let me just jump into this. So this is joined with my students and one collaborator from Spain, Andreas Winter. And also I want to say that feel free to ask questions, clarify doubts. So this is CSPL is a education seminar. So, feel free to ask questions. So we are going to have our ISIT, IEEE International Symposium on Information Theory next year in Ann Arbor. And I'm one of the co-chairs. So this is a little bit of advertisement for that, So we are, ISIT is coming to Ann Arbor after 39 years. So feel free to, talk to me, and then we can I can tell you more about this conference that's going to be held in Ann Arbor next year. Good. Let's now jump into the problem. So I will spend a couple of slides motivating the problem. So as I say, we're in the midst of a quantum revolution, and quantum computers aim to solve very complex problems that has a lot of applications, to our society with exponential speed ups. And most computing models are going to be based on qubits. Like classical computers are based on classical bits. These are going to be based on gate-based qubit model. And we are going to be working in the NISQ era. What that means, that noisy intermediate scale quantum. That means the quantum computers are going to be very noisy, unlike classical computers, and they are not scalable in the sense of recently I heard IBM came up with 400 qubit quantum computers. So we are in that regime, hundreds of qubits. And there are several competing technologies. I mean, we still haven't kind of converged on any one particular technology. So different groups are competing with the healthy competition toward building these kinds of computers with different kinds of technologies. But most are based on the qubits. So the quantum distributed computing network is basically a necessity, because we yet cannot build any scalable quantum computers. So at most we can build hundreds of qubits. So they need to be networked if you want to do anything interesting. That's one important concept. The second concept is so maybe I should move this panel a little here. Maybe there. Okay. The other issue is there are many quantum system applications which are not qubit based. For example, if you look at quantum sensing, which are based on optics, they're not like coming out of a qubit per se. Okay, so we use qubit based models because it reduces the noise and things like that. But most applications, for example, quantum sensing, a lot of applications, they kind of give quantum states which are not qubit based. That means, in fact, they are continuous variable quantum systems. Moreover, all transmission technology, to want to send qubits from one computer to another computer, we have to use optical system. There's nothing else. Okay, and all optical systems are continuous variable systems. So on one hand, all computers are using gate-based models. They're not mostly based on optics, but all transmission technologies are all based on fiber and things like that. And here is a picture of the argon taken from Argonne National Lab, where the problem is to do what is called as transduction. That is, convert quantum information from one form to another. Okay, so this is called transduction. So basically, that means we need to convert quantum information from one form to another. And so in that case, the most important thing that comes, or concept that comes to mind, is how to compress quantum data. It turns out even to just simply store the data, it's maybe a good idea to compress it, right? Because otherwise, you will have to protect those quantum information, which could have multiple variables, and in which case it will harder to kind of protect them. So if you compress it, it will be coming up with fewer qubits, which will be easier to protect against all the environmental noise. So compression has become very hot topic here, and this is the motivation for this talk. In particular, we are going to be looking at compression with loss, because continuous variable quantum set cannot be compressed like lossless. All right. So this is a brief overview of where the talk is aligned, and I want to say want to start with building some classical background. Okay, because we want to place it in some what's known in the literature. So next few slides are all going to be classical, and everyone should be able to connect to what we are doing. So this is let's go back to estimation, classical information under noisy observation. We have a signal X, and we have observation noise, observation Y, and it's passed through some channel, and the estimator wants to estimate the signal, right? It's applying some function. This is a classic estimation theory. And most approaches, if you see, they're all based on the loss functions, correct? Squared error, absolute error, what kind of errors that you can come up with. And we want to minimize the expected loss, correct? So as I said, this is we teach the EX301, EX501, and 564, and many other courses in 550, and so for example, for squared error, we know the optimum estimator, which is the conditional expectation. All right. So all of these things are well known. And one thing that we can do to extend this to kind of a large number of samples is to look at what's called the local error criterion, which is basically additive squared error. Correct? So we can just simply look at the square error of all the samples, add them, and divide by n. So we can call this as a local error criterion. Okay. So sometimes also called as additive loss criterion or whatever. So basically, if you have scalar rate variable, you just minimize the expected loss, it's a squared error. Otherwise, you just add all the losses and minimize. And I just put 1 by n here for convenience. Okay, guys. So it's well known. It's in the books and taught in graduate courses. Now, one concept that comes up in all of this is the posterior. The posterior is a bread and butter of system engineers, correct? So the idea in posterior is this. So I'm going to use a little bit of quantum technology here to talk about this. So the original viewpoint in any kind of estimation is that first signal is generated, then comes the observation according to this decomposition of the joint PMF. So P of X and P of Y given X. But Bayes uses an alternate viewpoint, right? And in some sense, it's surprising that it's an interesting the fact that he came up with this idea, and it's actually even surprising now when you look at it from this perspective, because Bayes says that you first generate the observation, and then the posterior distribute. You generate the signal out of the posterior distribution of X given Y. Okay, so it's just basically looking at the same thing from a different perspective. But from the quantum side, so here we have to keep track of what we have to do in terms of copying the signal, because in classical, what happens is you can copy information, without any remorse. As if there's no tomorrow, we can copy information all the time. So that means here, so signal is generated first and then goes through the channel to get the observation, and we can make a copy of that on the other side, and we can now talk about the joint PMF of the signal and the observation, and that's something that comes to us naturally without even realizing. The same joint distribution is now viewed in this alternate perspective in this way, right? I mean, let's think about it. Here is observation, and it has to go through the posterior channel to generate the signal, correct? But it's basically the same joint distribution viewed from two different perspectives. P of x times P of y given x, P of y times P of x given y. And this is all coming very naturally for us, so there is nothing big deal here. And most estimates are statistics of this conditional PMF. If you are using the squarer, it's the mean. If you are using absolute, it's the median, and so on. Correct? It's a well-known quantity. So this is also something that is used in information theory. So now I'm going to talk about the Shannon's perspective on the lossy compression. Like lossy, like estimation, we kind of use the same kind of idea. There is a healthy, interplay between information theory and estimation theory. Correct? So we exchange ideas. So here too, Shannon formulated the lossy source coding problem in the following. So there is a signal xn that needs to be compressed into bits. And here is the m or indices or m that is coming. This is the encoder. And then there is a decoder which is going to work with those indices to reconstruct the signal. Correct? Pretty well-known fact is taught in graduate courses, EX550. So here we have a block of signals X, and the reconstruction is exact. What is the problem? We want to compress. And this is our notation. So again, for quantum audience, I have to tell what that is, but for system audience, I don't need to tell what that is, right? Because that's a pretty standard notation. And of course, we want to compress below entropy because compression up to entropy is pretty easy and well understood. Of course, we are going to use a loss function now because we want to measure distortion, because we are not going to be able to reconstruct the source perfectly because we are compressing below entropy. So we are going to use a loss function like estimation theories. What loss function? Well, we're going to be using block error criterion, which is going to be local error criterion. So again, these are all well-known quantities, so it's good to take a perspective on this. Okay, guys. So we're going to use a loss function, which is a local error criterion, which is I'm going to shortly see what that is. And let's keep in mind that we want to compress it with let us say index m coming from finite set. Whether you want to represent that in decimal or binary representation doesn't matter. And we want to constrain on the rate, which is this rate r. Correct? All right. Shannon formulated this long time back, 1959. We want to minimize the rate such that, or for a given rate, minimize the expected distortion. All right, guys, everything is business as usual here. So again, let's take a look at Shannon's perspective, Shannon's problem formulation from this perspective. We have the source coming, which is assumed by IID, which is also done in most estimation theory works. It's some known PMF PX. I have a loss function, which we call distortion criterion, because information theorists have the habit of just take somebody's idea and then rename it. Right? So instead of calling it loss function, we call it distortion function. And then we use the additive distortion, additive in the sense that it's what we call a local error criterion. So that means xi is measured with its reconstruction and see how much is the loss, and then you add and divide by n, as I said, for averaging purposes. Correct? And we want to minimize the expected distortion. So here is the source, which is the n-length source, and then this is encoded and decoded, and we want to measure the distortion, which is with this function d. We don't even use L, we use d, because L stands for loss, right? And it will be below our dignity to use that, what's used by estimation theorists. Okay, so we use our own thing. So it's going to be d here, which is the distortion function, but it's exactly the same. We want to minimize this quantity, and we use a little bit of epsilon here so that we give a little bit of leeway. And eventually we want that epsilon to go to 0 because we are talking about asymptotics here. And Shannon formulated this problem and solved this problem. And we get what is called a single letter characterization, which is given in terms of mutual information between the signal and the reconstruction. So signal distribution is fixed. So we optimize this over all forward channels. X had given X, as you can see, is a forward channel that satisfy the loss function on a single letter basis. So look at one sample of the source. So this is the genius of Shannon, where he kind of, although it's an asymptotic problem, he characterized that performance limit using just one use of the channel or one use of the source. So we use one use of the source and we perturb that with a channel, forward channel, and measure the loss. And as long as less than D, we can evaluate the mutual information, and it turns out that's the minimum rate of compression. Okay, guys. So this is pretty standard stuff. So this is classical. And the loss criterion or the distortion criterion gives a way to compress it below the entropy. Okay, it admits single letter characterization, so all well and good. Okay, now comes the quantum. Let's see what's going on. So for those of you who are not familiar with the quantum, let me say a few things. First of all, there is something called no cloning theorem in quantum. That means quantum information cannot be cloned. Okay, so unless I tell you what the state is, you cannot look at the state and figure out what the state is. There's no way to do that. So it's called no cloning theorem. That means if somebody gives you an arbitrary state, and clearly also we should also keep in mind that like the way we have PMF, we have what's called density operator. Like a probability vector becomes a matrix now for the case of quantum states. So you're not going to be just describing one variable with a PMF, but with a matrix. And that matrix has to be positive semi-definite, has to have unit trace. So that means all the eigenvalues can be thought of as a probability vector. Okay, for those of you who are not seen this before, just want to bring you up to speed. If we can. So we kind of characterize the source with its density operator, and we typically use Greek letters here. And there would be some quantum channel, which will be some perturbation of that, and we want to see how to compress now quantum data, subject to some criterion, right? Like the way what is done in classical. But I want to say that quantum information is very physical, in the sense that since it cannot be cloned, it's just we have to kind of treat it like a physical, in a physical sense. So in the sense that we can't talk about input and output at the same time. So either you talk about the input or you talk about the output, because input becomes the output.
You cannot clone because there's uncertainty principle that you cannot
Yes.
position it simultaneously. That's the reason.
Well, the idea here is that when you say measure, I mean, when we want to say we want to clone, that means we want to make multiple copies of it. And there are several reasons why it cannot be done. The position and momentum is one reason, but there are more fundamental reasons why you cannot clone, because they are kind of very fragile objects. So you cannot, there is no operator that can take an arbitrary state and make a copy of it. That's it's kind of hard to explain in few sentences why it cannot be cloned, but cannot clone.
There is some fundamental.
Yes, there is a
Just
no, there is a fundamental limit. You cannot, So I mean, one simple thing is to say that you cannot look at it because it's going to get altered if you look at it. If you apply anything like trying to copy. Yeah. So no cloning theorem is a bottleneck. So nature takes away some things, but nature gives back. Okay, in a big way, in the following sense, that so as I said, input and output, this is one fundamental thing that we as system theorists have to grapple with. Because in system theory, there is input exists and output exists at the same time. No big deal. But in quantum, either input exists or output exists. They don't exist at the same time. Okay, so see what I'm saying? Yeah,
you cannot see the same time.
That's right.
See, but with delay. Here you cannot do it.
You cannot even with a delay. Yes, classically you could say with a delay because I could store it and then look back. Like for example, with somebody sending you information, you see the output, but then you can call that guy and say, hey, what did you send? There will be a little bit of delay, but even with delay, you can access that information because that person can clone that information and then keep it as a copy. But in quantum, every process has to be thought through from scratch. Okay, does it make sense? So input and output don't exist. So we can't talk about the joint PMF in the usual sense because, as I said, either input exists or output exists. They don't exist at the same time. But as I said, nature gives back something. And for information theory and even for system theory people, we need to have a copy of the information. Otherwise, how do we know how much loss is incurred in the process? Correct? This is a basic question. And what people do in this field is we use a proxy. What kind of a proxy? The proxy is what is called reference. That means instead of making a copy, right? It's basically what is a copy after all? It's a random variable that's perfectly correlated with the random variable that you have. It's a perfect correlation, right? So perfect correlation means mutual information is equal to 1, shall we say? For example, if it's a bit, yeah, we have one classical bit, want to create another classical bit, which is a copy, so the mutual information is 1, entropy is 1, mutual information is 1. So now we do the same thing in the quantum. What we do is we take this source, we do something called purification. That means we create a pure state in a higher space so that in the lower space, in the smaller space, it looks like a mixed state, like a density operator. So when we say here density operator, again, those of you who are not familiar with the quantum, you should keep in mind that if you have a pure state, there's no entropy there because you know what the state is. So the state has to be mixed in the sense of probabilistic mixing to have any entropy. That's why we use the density operator. So density operator basically characterizes that the fact that there is classical uncertainty in the quantum state. Okay. So we do what is called purification. So purification basically means coming up with another quantum state that's perfectly entangled now with the original state, with the state that you have. It's not correlated, it's beyond correlated. Because entanglement means that it's something really strange happens in quantum, which is that the joint system may have low entropy, whereas individual system will have high entropy, which is not seen in classical systems. So you can see here that partial, I'm going to now consider my state, my source A to be part of a bigger system, and the bigger system is pure state, and that has no entropy, zero entropy. But the state here, my state A, has entropy. You know, it's like what it's a one-Lyman entropy, which is basically Shannon entropy of the eigenvalues. Okay, so essentially what's going on here is that means the mutual information is basically 2 here, which is more than what's allowed classically, right? Because entropy of x plus entropy of y minus joint entropy, because in a perfectly correlated system, you have both of them individual entropies, 1, 1, minus 1, so you get 1. Whereas in quantum, the joint entropy is 0. So the individual entropies become 2. So mutual information goes beyond 1 in quantum. So basically, to make the long story short, what we need, nature gives you this additional degree of freedom, which is looking at the state from a higher space, which looks like a pure state, no entropy state. And that we can use as a proxy for the source. Because that nobody has access to, and that you can think of it as that is something sitting there, like in an abstract space, and I do all my operations on my source. I do the transformation, encoding, decoding, blah, 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 whatnot. And then I compare with what is going on on the top side, which is the proxy, because nobody has access to proxy. So that's the idea of reference, which is a very fundamental concept when you are doing information processing in quantum systems. Okay. All right. So that's why nature takes away the ability to clone, gives back. It's like giving really back. In the sense that it's much more stronger. When you have entanglement, you don't want perfect correlation because it's beyond perfect correlation. Okay. All right. So this is some little background information for those of you so that you can see why we bring this reference. So in some sense, reference can be thought of as a proxy for the source, which is perfectly entangled with the source that you have. So an example would be something like this here. So you have one qubit, which is with characterized with a density operator here. And in this case, it's a very simple density operator, which has just 1/3 and 2/3 on the diagonals, right? It has eigenvalue 1/3 and 2/3, right? It's a density operator. And the pure state that is created is going to be of this form. That means that state is going to be either 0, 0 or 1, 1. And it's not a probabilistic mixture. It's what is called superposition. Okay, so you can see here 1/3 plus √2/3 is not going to be summing to 1, but the square will sum to 1. So what's called a superposition. Okay, And we say this is an entangled state because this is more than just correlation. Okay, guys. So that's the some little background. So for those of you, so that you can kind of bring up to speed here. Before we go for any questions, does it make sense?
Like,
Which one?
this notation of psi within right brackets.
No, that's just how we define a state, quantum state. Like it's called ket, like a bracket, like it's a ket. It's part of the inner product. So you should treat it as a vector when it is given as a state. But when you take like outer product, outer product, right? So then you create a matrix out of that. So for example, you have this state like this. This is, you can think of it as a column vector, and if you do a row vector, you get the corresponding density operator of that state.
So this is mathematical representation of the process.
That's correct.
Physical, what happens? You take some signal, you process them, or you have two different signals, and somehow they are synchronized and they behave in a similar manner.
Correct.
What all of this means from the physical, physical quote unquote, what's happened with the objects here. Like we have a linear system, with there's in input, there's an output, we can define what this thing is, and we know what system is doing. This is its transfer function or the distribution. So what's happening here? You go from this quantum channel, and you obtain this purified signal. What's physically with it?
See, it is, yes, physically nothing is happening. The R is only for a mathematical construct. We only use that to for mathematical construct. Like the way we copy. Where do we copy? The copy is not going through any physical system. You see what I'm saying?
Yeah.
It's only for doing the analysis of your system. So for example, you're building an estimator, you want to look at its performance.
Right.
We send the input, we get the output, and we make a copy of the input. Right? So the copy is not going to be doing anything, even classically. It's not going to do anything in the sense of this is going to be sitting there. It's only used for analysis purposes. See what I'm saying? I mean, it's like now we have to kind of rethink some of the things that we have been doing. Like consciously what we are doing in some sense.
I think in physics, the people interpret entanglement as two completely different systems. But
yes,
they behave like one.
That's correct. They behave like one. Yes, it is exactly that. It's just that I can imagine a perfectly entangled state that is there in the universe. Right. That's entangled with this. This is what's called the purification. So it's kind of you turn this on its head, the entanglement, and say that now I have a mixed state. There is no mixed state, people say. Because what is a mixed state after all? It's a classical uncertainty. Right? So what do you mean by classical uncertainty? Because in quantum, then everything, you know everything. So it's a perspective, and the perspective that we have is, well, I'm only observing part of the system. There is some other part that is sitting there. So when I'm saying I'm sending these qubits, so I'm only measuring with respect to that. For example, in a quantum computer, you have some qubits that you want to send. And maybe you're only looking at half of the qubits, which are entangled with the other half, which will be sent to somewhere else. Now you're sending this part of the qubit, right? It looks mixed now, but together they look like a pure. So in an actual physical situation, you can have many cases where the purification could be real. It's just that it's beyond your control, just sitting there somewhere in the universe. Okay. All right. So I said that nature gives back in terms of it doesn't give you, it doesn't allow you to copy, which will give you something which is perfectly correlated. But who needs perfect correlation when you have entanglement, which is beyond perfect in some sense? Because mutual information 2, which even in your dreams, you will never see mutual information 2, correct? You'll only see mutual information 1. All right. So now, with all that background, we can now formulate the problem. And this is the problem of lossless source coding. First, let's check it out and how it is formulated. So you have some source. You can think of these as qubits coming from a computer, quantum computer, that needs to be sent somewhere else for doing further processing. And maybe all of them are not being sent because if you know what the state is, there is nothing to send, right? So because if you have a pure state, that can be locally generated wherever you want to send it to, correct? So we have some information which is modeled as a density operator. We want to encode it into qubits, compress, and then possibly at the later stage, want to use a decoder to decompress the information. And we want to formulate this problem, this almost lossless, and this was done a long time back, almost 30 years back now. So, quantum has been alive and well for 30 years at least, right? Okay, so here is the problem. We have the source and we want to encode it and decode it so that we kind of, make sure that it's the same information that you reconstruct. There is, as you rightly pointed out, there is uneasiness among some part of the community in using the reference. They don't want to use the reference at all because it's a mathematical construct. Okay, then you can formulate the problem, but it's going to be a little more complicated. With reference, kind of a lot of things come for free. So that's it. So the information theory community has readily accepted the idea of a reference. So here is the situation. So here is our source. This is our source, and this is the reference. So source is compressed into qubits and reconstructed. You're going to get some state. Now we can talk about the joint kind of PMF, joint density operator, because the references will be there all the time. And what we want is this state, the output state and the reference should look like the original state, which is reasonable, right? So what I am saying is, this is the original pure state, which is my source and its reference. This is the encoded and decoded state. It now may not be perfect, but it should be pretty close. We measure closeness with the trace norm, which is basically an operator norm, basically how these two operators are close. We don't need to worry about what that is exactly to understand the talk. Of course, when we are measuring qubits, we are looking at the dimension of that Hilbert space, the number of basis vectors that is used to reconstruct that information. All right, as I said, this 30-year-old stuff, so we should be moving on this pretty fast, right? So Schumacher showed that if rate here is measured in terms of qubits, if it's more than 1 Neumann entropy now, so 1 Neumann entropy is like the entropy, classical Shannon entropy of a classical source, where it's literally Shannon entropy of the eigenvalues of that density operator. Remember, I told you that the density operator is a characterization of that quantum source, which is a positive semi-definite matrix with the trace equal to 1. Positive, that means all eigenvalues are positive, they sum to 1. So if the rate is more than entropy, then there is a reliable compression, and they came up with reliable compression, and they showed that if rate is less than entropy, there is no compression. You can't do any compression. So now comes the issue of how do we do lossy compression? So now we need to look for a loss function, correct? Because like the way Shannon did lossless compression and then lossy compression, so we also do lossless compression first. That was going to be Schumacher, and then now we need to do lossy compression. So we need to come up with an analogous notion of a loss function, and that too, this additive loss function. In fact, people have looked at this for a long time. Okay, so already 25 years now since the first attempt at looking at this. This is by Barnum. He looked at something called entanglement fidelity. We don't need to know exactly what it is, but it is a measure of the loss. So in other words, basically what is the loss function after all? It's some kind of expected loss is basically, in some sense, is measuring how close the original source is to the reconstruction. Correct? So it's basically doing the same thing here. So if you now kind of eyeball this thing, so I look at what's called entanglement fidelity. It's like a fidelity we measure, which is 1 minus the loss. So typically it's much easier to do fidelity than the distortion. And our loss functions or distortion function is going to be typically 1 minus the fidelity. Fidelity is a measure of closeness, how close these states are. It's relatively easy to understand. So here is the original state, quantum state, and here is the encoded and decoded state, and we want to measure how close they are. Okay, forget about what is that, the mechanics of that. It's basically a little bit of inner product that's going on there. So this is a matrix and these are states, and you have to kind of get a real number, basically a complex number that will tell you what that quantity is. It turns out it's a real number basically. Some loss function for one use of the one source and one reconstruction. And of course, we will do the additive loss. Okay. So what is additive loss? Just look at each quantum state, what is happening in its reconstruction, and then do all these for n samples and add them and divide by n. This is where things starts breaking down. Because as Professor said, quantum guys, when they get entangled, they don't like to get separated. And in fact, if you want to compress any source below its entropy, you need to bring an entanglement. If you think about compression, what are we doing? You have a memoryless source. When you compress it, it has to have memory. See what I'm saying? Because the entropy has to go below the entropy, the entropy of the reconstruction has to go below the entropy, right? Because we are doing compression. So that means that your reconstruction must have memory, must have correlations. That's how we can create a reconstruction which has low entropy, because it has memory. What is the corresponding concept is entanglement. So it means the reconstructed state must have enough entanglement so that it is now having lower entropy. Moment you bring an entanglement, these guys don't want to get separated. Just like what I call true love. So in the sense that once you get entangled, they lose their individual identities. They give up their identity. So this is where things starts breaking down. Yeah, 4:30, right? Yeah. I mean, I'm going to be going slow here because I want to give the basic idea, but I'm not going to complete the talk. Don't worry.
Telling you ahead of time.
Yeah. He mentioned. Thanks for that. All right. So yeah, I'm not going to give you the whole thing. It'll be only up to 20 slides, basically. Okay. So as I said, we want to look at the additive loss. Additive loss means the encoding is done in blocks, because otherwise you don't get compression. That means you look at all n samples, do compression, you create entanglement, create a low entropy description of that source, and then you can get you satisfy the loss criterion. But what is the loss criterion? It looks a little complicated here, but basically what we have to do is we have to average out. So you encode n samples, you get n samples as the reconstruction, but then you look at xi and xi. What does that mean? That means averaging out other guys. We don't want that. Xi and xi. But these xi now they love their neighbor so much they don't want to get separated. So what happens is that it turns out it's going to be pretty bad for the problem. I'll tell you what that pretty bad means. So we can do the problem formulation. People did the problem formulation, and I have a picture for every slide. So that is the encoder and decoder. They're done in blocks, but you have to look at the corresponding distortions. For that, you have to go corresponding the corresponding references. You have to compare it, and then kind of do partial trace. Basically, partial trace here basically means averaging. Find all the losses, add them, divide by n. All right. There's no harm in formulating the problem, but the answer is, do we have a characterization of the performance? It turns out this is the result which was obtained by Datta et al. That is the rate distortion function, the minimum rate required for satisfying the distortion criterion. And if you see this, basically, it is an n-letter optimization. It means that there is no single-letter optimization. There's no single-letter characterization. Moreover, if you have an eye for this, it turns out it's a double minimization. That means you first look at the channel. So the channel is a k-letter channel because there is no singularization. You have to look at the k-letter, let k go to infinity, and this is basically incomputable. Okay, it's only for academic purposes. So we look at the distortion for k letters is less than d, and optimize over all forward channels, all encoders basically. That's like reformulating the problem itself. And then this is the rate at which you can compress that, to which you need to do an additional internal optimization. So that means we are not going anywhere with this. So it's an overly pessimistic problem formulation because, as I said, once you get entangled, you don't want to be separated. So what shall we do now? So we have to scratch our head enough times. So we have to go back to the classical problem and say, hey, can we reformulate Shannon's problem? In fact, can we reformulate the entire estimation problem without ever using a loss function? Okay. Also, in information theory, we have this channel coding and source coding perspective, and it also doesn't kind of nicely kind of become compatible because in Shannon's case, he also characterized the capacity of the channel that also came out as mutual information. Here, people have formulated the channel capacity, and they get something called coherent information as the capacity. Even there, you don't get a single letter characterization, unfortunately. But here we are not even getting that. So that means this idea of a packing versus covering perspective is also getting lost. Because in source coding, lossy source coding is like a covering problem, and channel coding is like a packing problem. There's a nice duality between the two, and this is observed for at least a century. People have written on this, for at least 100 years. So even that is lost because we have a nice packing perspective in channel coding, which is quantum, error correction codes, whereas we don't even have that in the case of covering. So we have to kind of rethink our approach. So we go back to classical. So now the question is, which everyone here can appreciate without having, if you don't have any background in quantum, you can still appreciate it. So what I'm now saying is, I don't want to use a loss function, which is a local error criterion, because I have to do averaging. The unwanted x hat i's I want to throw away because I have to average up, which is not possible, which is highly avoided in quantum. So the question now is, I'm going to ask you, hey, can I formulate Shannon's like a lossy source coding problem without the loss function? And how do we do that? For that, we can look at this result, one small result, which says that if you look at Shannon's problem, it's been well studied. As I said, 1915, almost 60 years, 65 years. So people have kind of beaten it to death. So they look at all possible situations and all kinds of structures that could be inferred, they have inferred. Although you're optimizing the forward, this is Shannon's classical. It turns out the reverse, the base posterior channel takes the center stage as expected. Right? The Bayesian perspective, map estimator, everything is based on posterior. Here too. Moreover, if we now think about what happens in a lossy source code, let's be honest about ourselves and look at a lossy source coding. What is lossy source coding? Basically quantization. If you have some source and you quantize and ask the question, suppose if I give you the quantized version, how does the source look like? Posterior. That's posterior, right? Posterior says, hey, I have this observation. How does the source look like? What is the uncertainty in the source? So the source is not deterministic. It is random. It is a product here. Encoder is non-product because we did the quantization, right? Block quantization. Here, I just do a two-dimensional quantization for your illustration. But if you think hard on this, you can see that if you do the quantization well, if you do a good quantization, then given the reconstruction, the source should be nearly like a distributed on the surface of a sphere. See what I'm saying? It's like a packing spheres, right? Quantization is all about packing spheres. So that means that covering basically, that means given a reconstruction, the source should look like it's distributed on the surface of a sphere. That means the source posterior, although the encoder is done in blocks, the source, if you look at the backward, this is just the posterior, right? So we had this result when I first landed here in Michigan, 2004. We have made this observation. Hey, look, for a good code, this happens. What happens? The posterior becomes memoryless. People said that, hey, this is all for, this is well known. Everybody knows this. There's nothing big deal. So I published a conference paper. But if, I didn't want to publish a journal paper because the people say, hey, this is all well known. But this came handy for us in formulating the problem. So what is going on here? What is the lesson? The lesson is when you do a good quantization, doesn't matter what kind of loss function, the reverse channel or the posterior channel looks always memoryless. Even though the encoder is done, encoding and decoding is done in blocks. That's the secret of the universe in some sense. Okay. So that is the whole point, that your posterior becomes memoryless. Like a memoryless, a product channel. Now I'm going to hang on to it, because when I saw this distortion is not working out, I was pulling my hair out. Hey, what's going on here? And fortunately, my earlier work, became a savior in some sense. And I'm going to formulate now. And then there were several follow-up work actually after that. There was a 2005 work, and then recently 2015 there has been some follow-up work. So people found it interesting after all. So here is my problem formulation. Now, this could be used for even estimation theory, but I'm formulating the problem for the lossy problem. What is the problem? I have a source, and I'm going to specify the posterior channel. So this is the well-known result. So let me go to the problem formulation here. Okay, so here is the problem formulation, guys. New problem formulation. What is the problem formulation? We're given a source, it has some distribution. Now I need a loss function. I'm not going to give a loss function. I'm going to give a channel. Posterior channel. Posterior distribution. You design your encoder and decoder so that your posterior looks like this. Why not? Posterior we've been banking on posterior for doing all kinds of estimation. And all statistics of posteriors are our estimates. So I'm going to say, hey, look at this. This is your encoder and decoder. You cannot touch the distribution of the source. That is fixed, like a Bayesian. You can do anything you want, encoder and decoder. Your encoder and decoder should be such that your posterior should be memoryless. So here is a picture. So this is your original system. This is classical, so you can make a copy of it, encoder and decoder. And now we apply the Bayesian perspective. This is the reconstruction, and then the posterior channel for any transformation. That posterior has to look memoryless. That's my constraint. What channel? The channel could be something that could model a practical situation. For example, in the case of Gaussian case, instead of saying squared error, I'm going to say that the posterior should be an additive at Gaussian channel. Indeed, for squared error, it turns out the posterior distribution, which was sometimes also called the innovations, is actually Gaussian and additive, in fact. So why don't we formulate now the lossy source coding problem without the loss function, but with a channel, saying, hey, do whatever it takes, but your posterior should look like what I'm going to, what I command you to have. And that's the innovation that we do. See what I'm saying? And this is exactly the motivation coming from what happens in a good code, in a lossy case. Because Shannon said, okay, use the loss function. Because everyone was using loss function. Entire estimation theory is built on loss functions. So, but posterior is very important, right? So why can't we now say, hey, design your system so the posterior should be looking like the one that I want, that I want. That's the new take on this. So it's a nice formulation, and we are now using that actually on estimation theory now, because even classically it's not been done, for heaven's sake. See what I'm saying? So it's a motivation that came from quantum because your loss function didn't work. So now we have a new problem formulation in lossy source coding that could also have consequences for just regular estimation theory, classical estimation theory. You see what I'm saying? So we've been now debating as to how to kind of shall we say formulate this, and uncover any kind of hidden structures and stuff like that. And nature is kind to us here. So we formulated this problem classically, and we found, as usual, mutual information as the performance limit. Okay, because anyway, they are kind of equivalent in the case of the classical. Moreover, we have also formulated the quantum problem. So I have now let 422 here, so I can speak for another 4 minutes, I guess. Okay. So now I'm going to tell you the quantum version. So we have the source and its reference, because that's a proxy. You do your encoder and decoder, want to compress it into qubits, so that you get this reference and reconstruction. Now we can come up with a posterior. So there is a concept of a posterior now, which I haven't told you about in the quantum, but one can come up with a posterior. So we came up with this idea of a posterior. That means that the same state can be viewed as if the reconstruction is there and you make a reference of that. That is going through some quantum channel. I mean, it's not that hard to kind of comprehend that is whether that is possible or not. Okay, it is possible. So that means for any, so here you can see this is like a forward channel encoder and decoder. Now you can look at the same thing from a base perspective, but it's now quantum base perspective. Here now I'm entangling the reconstruction with its reference, because originally the source was, we used the reference of the source, is the source and its reference. They are entangled here, whereas here the reconstruction is entangled, and that is going through a reference channel. That's like a posterior. I'm going to claim that you want that to be close to a product channel, like what we did in the classical. Okay, that's basically what it is. This is the first term, and this is the second term. I want that these two terms to be close. So that means that the source going through the forward channel, forward transformation, you apply the like a base perspective, get the reverse or a posterior channel, and a posterior has to be product. Of course, we want it to be close, the usual channel thing, and we minimize and try to get an asymptotic characterization. And to our surprise, this is the problem formulation. So since our time is up, I'll be just mentioning the result here in the next slide. Fortunately, nature has been kind, and we got a single letter characterization. And the answer is coherent information. This is what's called coherent information, which is not a mutual information. It's another information quantity. But what is surprising is that it is a single letter characterization. See what I'm saying? So we don't even have a single letter characterization for the capacity. Okay, but we have a single letter characterization in this version of the problem, and it is exactly like the covering perspective. Okay, so it can be interpreted. I have one last slide here, which is a picture. If I can come to that, yeah. So the idea here is like literally like a covering, right? I mean, quantization of lossy source coding is all about covering. So it turns out if you have some state and you construct it kind of interestingly, it turns out it can cover some region of the source space, and that is basically we can measure it with some entropy, like entropy of E. And I don't have time to say what E is here, but it's some other variable that comes along. This is the source space, and its entropy is the entropy of the source. I'm using H here, and then you just have to pack that enough, like cover that with enough box so that the entire source is covered. So the rate would be entropy of B minus entropy of E, and that's coherent information. So we have here coherent information. So it's kind of the proof is in the pudding, shall we say? Because if the nature is if it's not a good formulation, now we have to kind of justify why it's a good formulation. See what I'm saying? Because people might say, hey, that's some problem formulation, that who knows that whether that's the right formulation. But the proof is in the pudding in the sense that we get a single letter characterization. If the nature didn't like it, it won't have given us a single letter characterization in some sense. See what I'm saying? Because even capacity, which is formulated along Shannon's lines in quantum, that we don't have a single letter characterization. Okay, maybe with that I will stop. We have 5 minutes, but if anybody has any questions, I'll be happy to take it. Yeah. Any questions?
We want to take it outside.
Yeah, maybe we can take it outside. Yeah, thank you. Sure.